Example 1, I'll keep it one-dimensional here. F of x equals to, x cubed. So if we put y equals to x cubed, solve for x, what do you got? We get cube root of y equals to x, right? So f inverse of y is the cube root of y. So there you go. There's an inverse map for a function, and we didn't even have to do anything. We need calculus. We need anything, right? Great. Huh. Curious. So definition, and I mean, I'm not going to give full definition. Let me just say, we want for f, which is from some subset of, well, I guess I just say from Rn, but sorry guys, I'll make up my mind eventually here. So from Rn to Rn, to find something like, f restricted to, like f sub s, a mapping from s to, let's say, f of s, where f of s of x is simply equal to f of x for x and s, right? That's what we want. We want to find a subset that if we restrict the mapping to that subset, the function is invertible there. So such that f sub s is injective, right? And indeed, there's a g, which is a mapping from like f of s back to s. And what's the deal? Well, f sub s composed with g should be equal to something, and g composed with f sub s should be equal to something. You guys tell me what those are. If these are really inverses. I'll help you out. Identity, but on what and on what?
The identity on f set s.
F of s for this one, right? S for the other one by process of elimination, right? So that's what we mean by looking for a local inverse for a mapping. We want to find a mapping rather, f sub s, that if we restrict the domain to that s, then we've got an inverse, right? At least with respect to that restriction. And again, by some advanced calculus that I'll prove next semester, my apologies, I just have to bring in some ideas from another course here. If we take the differential of these relations, we get that the differential of s composed with the differential of our proposed g must be equal to the differential of the identity, right? But the differential of the identity is just the identity, by the way. That you'll prove in the homework because the identity is a particular example of a linear transformation. So what does this say? What does this say about the determinant of the differential of that and the determinant of the differential of g? Right? It would seem to say that the determinant of the differential of g should be equal to 1 over the determinant of the differential of f, right? Because, by the way, f and f sub s are the same. So at the points where we'd like to think about, this is what we'd expect, right? So what condition are we going to need what conditions are we going to need in order to, find an inverse? What should we expect? It looks like we need a non-zero derivative, right? We need the determinant. This is the Jacobian, right, if in the other language? Yeah? We should need the determinant of the Jacobian is non-zero, yeah? So, and of course, in the one-dimensional context, what's this look like? In the one-dimensional context, this just looks like what? The, basically the derivative with respect to x of f inverse, right, should be equal to 1 over the determinant, like df dx, right? At appropriate points. So one-dimensional, yeah? So surely if the mapping is invertible, right, it must have a non-zero derivative. This argument right here, right? Okay. df dx
Just waiting for your counter that much, like, you shove it.
is that as ddx of x cubed is 3x squared f prime of 0, 0, not equal to 0. Wait a minute, I mean, which is 0? It's 0, you know, so yeah. Huh. But I just found the inverse. One of your homework problems is to explain to me why this is okay.
Is it because you don't give the identity that way, so it doesn't work anyway? If you take like f inverse of 0.
No, this is, there's no flaw in the algebra here.
No, I mean like if you take f inverse of 0, that doesn't give you, or f inverse of f of 0.
No, I mean, it is true that f inverse of f of x is equal to x, and that f of f inverse of y is equal to y for all x and for all y. And in fact, the domain and the range for the cubic, they're both the reals, so no, these are genuinely global inverses. And this is really the case that the derivative is 0 at 0. So I'm just going to let that sit there. That's one of your homework problems, is to figure out what's not wrong about all this, because it seems like something's up there, doesn't it? Okay, so anyway, if we can set that aside and go on. What was Newton's method? Do you guys remember last time? So basically we could look at it this way, right? Y equals to, let me stop writing. We don't have forever, so let me get to the point here. Oops. I'll give you a hint. Do you guys want a hint, or do you want to think about it?
And what?
And what's the deal with what's going on there?
I don't want to hint.
You don't want to hit yet? Okay. No hint yet? All right. I will stop. I'm not very good at giving partial hints, as you guys know. So it's one of my many weaknesses. Partial hints are not really my forte. So, all right. Here we go. So we just went through all this. My next example is also a cautionary tale. I'll try to go through it quickly. Suppose we had the mapping f of xy is x squared minus y squared 2xy. In complex notation, this is just the f of z equals z squared map. If you calculate the Jacobian, you get 4 times the modulus of z squared. So this mapping got a non-zero Jacobian everywhere except the origin. So you might think that it would be invertible on the punctured plane. But we know that's not the case, because when you try to work out the algebra, right, and it's useful to use the polar form of a point in the plane. And all I'm doing, let me just to talk you through this. All I'm doing is I'm working out the principal square root formula. I'm just working out the principal square root formula. And when I do that, I show that, in fact, if you look at this point and you look at that point, they both map to this point. All right? Which shows you that the mapping's not injective. And then I'm actually building the formulas for it. This is partly to help you with a homework problem, which is similar, but based on z to the fourth. I don't actually come out and say that in the homework, so that's a giant hint. Don't tell Jack. So, Jack told me he was going to study for the subject test, and I just responded with like one sentence. It's like, well, as Dr. Sprano is often known to say, we all make choices. I just thought I would leave it there. Of course, I'm happy he's studying for the GRE, but
It's true.
yeah. So if you sort through the details of the algebra, you end up with this is the formula for the inverse function. It's the square root of the square root of x squared plus y squared, the exponential of I times the standard angle over 2. This is the formula for the inverse to that map. With respect to the the half plane, the slit plane. So yeah. And but there's a more obvious way to show that the square map is not injective on the whole plane, right? If you just think about it, as long as you're including antipodal points like z and minus z both square to z squared. So as long as your domain includes things on diametrically opposed sides of the origin, you can't hope to be injective. So the square map can at most be injective on like a half plane, because not even that, because you can't include antipodal points on the opposite ends of a diameter. And you could think about how that generalizes to other powers. But anyway, this is complex analysis, of course, but you guys have had that or are experiencing it. So yeah. So my point in all that is just, even if the Jacobian is everywhere invertible except for one point, that doesn't mean that you get a global inverse. All right? And the other cautionary tale shows you that there exist invertible functions where the differential is 0. What's up with that? But anyway, here's what we can say. This is the inverse mapping theorem for maps on Rn. Suppose you've got a mapping continuously differentiable in a neighborhood of a point P, and suppose that the determinant of the Jacobian of that map is non-zero. Then F is locally invertible at P. Indeed, there exist open sets U of W and P with element of U, and V equals to F of U with F of P equal to Q in V, and an injective map G from V to U such that G of F of X is X and F of G of Y is Y for each X and U and each Y and V. Moreover, the local inverse G is the limit of the sequence of successive approximations defined inductively like this. This should be directly reminiscent of last class where we talked about the inverse function theorem for one dimension. It is verbatim the same result. Just now for maps, and instead of having a derivative, dividing by a derivative, we're multiplying by the inverse of the Jacobian. This is, I think, very cool. And the proof of this requires every ounce of everything we've done today. Which is why I'm not joking when I told you I cannot write it out. Like, I have to project this proof. I cannot write it out without taking 2 weeks. Because every class I'd have to spend a half of the class reviewing what I've forgotten from the last class, So, anyway. So, before we prove the theorem, we prove a lemma. A wee bitty lemma. The inverse mapping theorem at 0 is what I'm going to call this lemma. It says, suppose you've got a function continuously differentiable in a neighborhood of the origin, such that the differential at the origin is the identity. And further, suppose that the differential at x minus the identity max norm is less than or equal to epsilon, which is less than 1 for all x in the R cube. Then the 1 minus epsilon R cube is contained in the image of the R cube under F, which is contained in the 1 plus epsilon R cube. And if you set V as the interior of the 1 minus epsilon R cube, and if you set U as the interior of the intersection of the R cube with the inverse image under V of f. Keep in mind that this does not assume the point. Here we're talking about the set theoretic inverse image. This is in no way a circular thing. Okay, so then f from u to v is a bijection. And bijection? A bijection. And the inverse mapping g from v to u is differentiable at 0. Moreover, g is the limit of the sequence of successive approximations defined inductively like so for v. Now, you can guess that if something is appearing as the limit of a sequence inductively defined, what is going to provide this successive approximative sequence and the limit point? What's it going to be? What did we prove last class? Newton? Well,
The contraction?
the contraction map. Banach's fixed point theorem is what's going to be it. But the funny thing is, in my opinion, is as we study these applications of Banach's fixed point theorem, the actual use of the fixed point theorem is the simplest part of all of this. Like, the setup is so much harder than Banach's fixed point theorem itself. Anyway, so here we go. If we apply the corollary with L equal to the identity and x and y in the cube, we get f of x minus y minus, x minus y, norm, max norm is less than the max norm of that, times the maximum of the differential minus the identity. Notice that this is, he's looking at this as L of x, L equal to the identity here. That's where that's coming from. And okay, so then we're back to that usual step we make, which is that if this is less than or equal to that, then we get that 1 minus epsilon times that, less than or equal to that, less than 1 plus epsilon. I just skipped the details this time because we've done it twice already today. So we get that. The left inequality, rats. Poor page breaking. So the left inequality here, what would, if x and y are distinct, right? Could f of x equal to f of y? X and y distinct. That would make this non-zero, right? If f of x equals f of y, this is 0. But this is positive. Can we have something positive less than 0? No. So this left inequality implies injectivity. And the right inequality shows that f of the r cube is a subset of the 1 plus r cube. It remains to show that the 1 minus epsilon r cube is a subset of the image of the r cube. This is the part which requires the contraction mapping. So define phi. First of all, let y be a point in the 1 minus epsilon r cube, and define phi from Rn to Rn by phi of x is x minus f of x minus y. We wish to show that phi defines a contraction mapping of CR with fixed point x. I guess fixed point is one word now, for which f of x equals to y. All right, so here it is. Max norm of phi of x is literally that, triangle inequality, as promised. And then what's this? Remember, f of 0 is 0, and df sub 0 is the identity. So this is literally x. So this is just straight equals to that. I don't think I technically need a less than or equal to here. I think I could actually put equals here at the moment. I think that's actually an equals. The next step is a less than or equal to, because I'm trading this for that. That's the corollary 1.4.26 we saw earlier. And then, but by assumption, this is less than or equal to epsilon. And that is less than or equal to 1 minus epsilon r, because we picked y in the 1 minus epsilon r cube. So because of where y comes from, we've got 1 minus epsilon r here. And because of the assumption that this norm is less than or equal to epsilon, we get r epsilon here. Because the norm of x naught is equal to r, because x is in the r cube, which gives us r. Oh, cool. So that means that what? I mean something. It means that phi of x is in the R cube is what it means, because its norm is less than R. So apparently the image of CR under phi is in the interior of the R cube, provided we construct y using that. Provided we construct y from the 1 minus epsilon R cube's interior. Therefore, phi of CR is a subset of CR. That's important because CR is a closed set. So we can look at phi possibly as a contraction mapping on the closed R cube, which is what we need. The contraction mapping theorem required a closed set. And then, of course, the actual proof of contraction is pretty simple. This by construction is equal to that, and that is less than or equal to epsilon times y minus y naught. Phi is a contraction mapping on the R cube with contraction constant epsilon, so by Knox's fixed point theorem applies, and there exists x in CR for which phi of x equals to x. And that means that x minus f of x minus y is equal to x, which is tantamount to saying f of x is equal to y. Uniquely so, which means we can use this to define the inverse. G inverse of y is x. But the thing is, this can be done for any y. We did this for a particular y, right? But this argument can be repeated for other y's. And as such, we can string those together and form the inverse function. All right? So I'm going to skip past this a bit because we're kind of out of time. But all that's really saying is that the open neighborhood stuff makes sense. That well, anyway, so here I define U as such, and I define V as such. Those give us the open neighborhoods. And as usual, the Banach's fixed point theorem defines the iterative sequence defined by the contraction mapping gives us the fixed point as its limit, which gives us this here in this context. And then what remains to show was the remaining claim was that, are they trying to get in here or something?
Oh, we're looking in.
All right, whatever. But
We're glass.
yeah. What remains to show is that G is differentiable at 0. So that's a little bit sneaky, but basically we already have that, and so he puts y equals to 0 and x equals to g of h and h equal to f of x and plugs them up into here. And after a little bit of sneaky business, we end up with the inequality that g of h minus h is less than or equal to epsilon over 1 minus epsilon times the norm of h, which gives us that the difference of g of h minus h over the max norm of h naught is less than or equal to that. But the thing is, if you go back and look at the argument, you can make epsilon as small as you want, which allows us to prove that the limit as h goes to 0 of this is 0, which is what we need to prove that g is differentiable at 0, with differential of g being the identity matrix. That's what we need to have here, because going back to my chain rule argument I covered up, if the differential of f is the identity, then the differential of its inverse must also be the identity by the chain rule. And that's what this ultimately proves here as we study the squeeze on that. There's a little bit of sneaky stuff there. Anyway, so that proves the lemma. And with our lemma done, then we return to the theorem. And the way to prove the theorem is basically by a sneaky trick. And so I'll draw a picture over here. Let me go make sure they don't have a class in here or something stupid. Is there a class in here or something?
There's an event that is starting in a few minutes here.
Oh, okay. All right, well, I guess we'll stop it here. There's some stupid event. Actually, I will make a video for the remaining 10 minutes a little bit later today and post it, hopefully. Sorry, guys.